Anisha ma'am, can we start,
Yes,
ma'am?
ma'am. Yes. Yes, we can start, ma'am. I think some more are there to join. That's why we just waited.
Ma'am, we could start.
Yes, ma'am. Then we can start. Good evening to one and all present here. Research is to see what everybody else has seen and to think what nobody else has thought. Albert Sent. With immense joy and a deep sense of scholarly spirit, I am delighted to welcome you all to the Faculty Development Program on From Models to Manuscripts Structural Equation Modeling for High Impact Publications, organized by the Department of Professional Accounting and Finance under the School of Commerce, Accounting and Finance, Kristu Jayanti University, Bengaluru. Before we begin, let us invoke the blessings of the Almighty to guide us in our pursuit of knowledge and wisdom. I request everyone to join for a moment of silent prayer. Thank you. This FDP is designed to provide enriching hands on learning experiences on structural equation modeling using AMOS, empowering educators and researchers to transform conceptual models into impactful, high quality manuscripts. It is my privilege to extend a warm welcome to our esteemed resource person, Dr. Ramesh Babu T, Assistant Professor, Department of Psychology, Central University of Karnataka, whose expertise will undoubtedly illuminate our academic journey. I also extend a heartfelt welcome to Dr. R. Vijayakumar, Dean, School of Commerce, Accounting and Finance, and Chair of this Faculty Development Program. A warm welcome to our co-chair, CA Dr. Annie Stephen, Head, Department of Professional Accounting and Finance, and to Mr. Jagadish KK, Coordinator, Department of Professional Accounting and Finance. I offer a cordial welcome to all the participants, faculty members, research scholars, and academicians from across India who have joined us virtually today. Your presence and enthusiasm truly enrich this occasion. Before we proceed, I kindly request all participants to follow a few important instructions to ensure a smooth and enriching FDP experience. Please keep your microphones muted throughout the session to avoid background disturbances. You may turn on your camera if your network permits, as it enhances interaction and engagement. For any questions or clarifications, kindly use the chat box. Your queries will be addressed during the Q&A session. Ensure you are logged in with your full name for attendance and certification purposes. The session will be recorded for academic reference. By participating, you agree to be part of the recording. Kindly stay connected till the end of the program to receive the feedback link and e-certificate details. Now, without much delay, let me introduce our resource person. Dr. Ramesh Babu is an accomplished scholar and researcher, currently serving as an assistant professor in the Department of Psychology at the Central University of Karnataka. He holds a PhD in applied psychology from Pondicherry University, with his research focusing on color preferences, color emotion links, and personality traits. With rich teaching and research experience at reputed institutions like Christ University Bengaluru and National Institute of Youth Development, he has contributed immensely to the academic community. Dr. Ramesh Babu has published widely in UGC KS Corpus and Web of Science Index journals, covering topics such as cyber victimization, adolescent mental health, caregiver burnout, color emotion research, and psychological assessment. He is also a passionate academic speaker known for delivering insightful workshops on factor analysis, structural equation modeling, statistical methods, forensic psychology, and various areas of mental health across India. Dr. Ramesh Babu is an active member of professional bodies such as American Psychology Association, the Indian School Psychology Association, and the International Society of Political Psychology. Sir, we are truly honored to have you with us today. Once again, we welcome you. Now the session is yours. Over to you, sir. Thank you, everyone, once again.
Thank you, ma'am. Hope I'm audible.
Yes, sir. Yes, sir.
Uh,
It's clear.
first, First of all, I would like to thank you, the organizers, Chris Jayanti University, especially Dr. Anisha ma'am and Dr. Annie, head of the department, and the Dean Dr. Vijay Kumar. Um, Thank you for having me today here. We planned, before I start the session, I would like to give you a small change in the schedule. As per with the permission from the organizers, we actually scheduled each day 1 hour from today to 22nd. Due to my other commitments on this month, 21st and 22nd, I would like to extend 1 hour to 1.5 hour each day, which means from today, next 4 days. So I would like to complete the whole module, whatever we have planned for this FDP. I hope this little arrangement is okay for all of you. Um, with having said that, let me straight away start with the agenda, what I would like to say about the structural equation modeling. So let me share the document here. Is it visible?
Yes, sir, it's visible.
Ma'am, is it visible to the full screen or?
Slideshow you can put, sir, then it will be visible.
Okay, fine. Yeah. Thank you once again. The whole FDP is all about from models to manuscripts. So structural equation modeling for high impact publications. So this whole FDP I have planned for 6 sessions. These are the session details. Today we'll start with the Amos basics, introducing Amos interface software, as well as theory part about this sum foundation. From tomorrow, next 3 days, along with the theoretical aspects, we will be practicing path analysis tomorrow, and day after tomorrow, structural this confirmatory factor analysis, which is both measurement model and structural model. And the last day, we will be doing the hybrid model, which we call it as a full model, and followed by any refinement and advanced sum techniques. And at the end, we'll be having publication report, ready reporting, which means what are the indices from the output that we can take it forward and show to the authors, like for the reviewers as well as the our audience, especially the publishers. So, with having said, the first session, though we are not going as a session wise, as I mentioned, I will be covering session 2 as well. In this session 1, I would like to start with the introduction to Amos graphics. A few basic concepts, like in the regression, in the structural equation modeling language, we tend to use the variable like exogenous variables and versus endogenous variables, and few components of the graphics, Amos graphics. Especially there are icons which we should be knowing about it when we wanted to practice it, and as well as the drawing simple path diagrams, because all the sum analysis we wanted to use it. Before we actually use it, we need to draw path diagrams. So like how to draw observed variables and how to draw latent variables. So this is what the session 1, and followed by session 2, which is about the introduction to structural equation modeling, characteristics of the structural equation modeling, and the two types of structural equation modeling, which is measurement model and the structural model. So this is the whole agenda. As you know, the introduction to the Amos graphics. Amos is an acronym for the analysis of movement structures. In other words, we can say, which is the analysis of mean and covariance structures. So a lot of us knows when the moment when we hear the Amos, most of us know about only Amos graphics. But actually, this has got 4 different modes of model specification, such as we have Amos graphics approach. We are gonna use this Amos graphics approach to learn about the this modes of model specification. And we also have the other mode like tables view approach, and also Amos VBNet approach, and Amos C hashtag approach. So these are all different versions, but what we are gonna use it for the next 4 days is the Amos graphics approach and little bit of tables view approach. Wherever possible, I'll also show this tables view approach because it's part of Amos graphic approach. And if you wanted to learn Amos VBNet approach and Amos C hashtag approach, I think I'll suggest at the end of my sessions, all 4 sessions, I share the material, the textbooks which you can actually go through and learn about the other two approaches. So the if you the choice between which Amos modes which I would like to use, though because I mentioned there are 4 approaches, that depends the choice of which Amos method to use model specification is purely arbitrary, and it depends on how comfortable you feel in working with either of the graphical or a table interface. So the most of us are very much comfortable with the graphical approach, and almost uh, it's well designed. It shows that estimates to be displayed graphically. So that's the reason the most frequently used technique is the Amos graphic approach. So here, as I mentioned, there are two important terms which we regularly use when it comes to the structural equation modeling, which is exogenous variables and the endogenous variables. So is nothing new, only the term is different, because when it comes to exogenous variables, which is basically synonym with your independent variable. So basically what we expect is our independent variable cause slight fluctuations in the values of any other latent variables in our model. So what we look for here, any changes in the values of our exogenous variables are not explained by the model. Rather, we can say that they are influenced by other factors external to the model that in few seconds we'll come to know, like measurement error and the random error. Whereas the endogenous variables either directly or indirectly. Uh, so here, this is how the components of Amos graphics looks like. Like so, for example, when you use it, when you open your Amos graphics interface, so these many icons are there. So I would like to show the icons by just opening the actual Amos. Then I'll come back to the theory part, because these all icons are very, very important, though very few we'll be using, especially we'll be using only 4 important blocks, what we call it as a building blocks. So for example, though we have several icons in the Amos graphic approach, there are 4 geometric symbols which are very, very important to us because we use frequently, because it has got a lot of meaning. So for example, if you see, we use either circles or ellipses to present the unobserved variables, or what we call it as a latent variable, or we can also call it as a factors. Uh, Whereas we also use these squares or the rectangles to represent observed variables. Whichever variables, say for example, observed variable meaning a question in your survey design, survey questionnaire, or whereas the unobserved latent factors, say for example, when we wanted to measure intelligence, intelligence cannot be measured directly. So there are ways to measure intelligence. So intelligence here becomes a latent factor, which is unobserved latent factor, whereas the ways that we measure this intelligence is what we call it as an observed variables. So observed variables, we use the rectangles, whereas the unobserved variables, we use the either ellipses, what you call, or a circles. Then also the most important, the geometric symbol is the single-headed arrow, as I mentioned here. So the single-headed arrow basically represents structural regression coefficients, and which indicate the impact of one variable on the other variable. So for example, when I say X, directed arrow to Y, so here I'm looking at the impact of X on Y. Similarly, you also have the double-headed arrows, which represents the covariances or nothing but correlations between several variables. So before we move on, I would like to show the actual interface. So let me know whether you can see this interface. Let me share my, yeah. So is it visible, this interface? Anyone?
Yes, sir.
Anish?
Yes, sir.
Yeah, yeah.
It's visible.
So look at this, as I mentioned here. You need not to remember anything clearly, because the moment when you put your cursor on this, any of those icons, it will clearly mention what this icon is. So for example, as I mentioned here, when I click on the icon, this rectangular icon, it shows that they draw your observed variables, right? Whenever you have observed variable, if you wanted to showcase, you click on this, double click, like in this, you can actually draw this. Similarly, you see the second icon, which is ellipse or oval shape icon, which shows for the unobserved variables. So you have this indicator. Remember, when you put your cursor, it says draw a latent variable or add an indicator to a latent variable. So here you have the single-headed arrow. Here you have the double-headed arrow. So here you have the error icon. So here, when you click here, it shows the captions. So when you click here, if you wanted to give a caption to your figure, it can be editable after clicking. So here, when you click on this particular icon, it shows us a list of the variables in your model. So the next one, the list of variables in the data set. So once you highlight your data set using either Excel or SPSS. SPSS would be more appropriate. So when your data is in a SPSS, when you download it in the Amos, it shows that the list of variables, what are the list of variables are there in your data set. Similarly, you have this particular icon for duplicate icon. So for example, when you wanted to draw multiple observed variables and the unobserved variables, when you find it difficult to draw multiple observed or unobserved variables, it is quite difficult. So what you do is, once you make one observed variable or unobserved variable, you can duplicate n number of times. So every time you right click on it, it will generate multiple duplicate icons. Similarly, you have this move icon. So for example, when you put one particular variable, if you wanted to bring it to the middle of this sheet, then you can place it anywhere. So you use this particular icon for a move icon. Then this is for the erase icon. Whichever variable you draw or you think you are not drawn properly, you can use this particular icon to erase this. And you also have this shape icon, and this is what we say rotate icon. You can rotate your figure differently, or observed or unobserved variables. And similarly, you also have the reflect icon. So what is this reflect icon? Is basically reverses its direction of an indicator variables. So left to right or top to bottom, you can do this particular using this particular. And this one can be used for move parameters icon. This is for scroll icon. This is for touch up icon. So you can actually enable rearrangement of the areas. Similarly, you can have you have select data files. So after clicking this, if I wanted to select file which is there in my system, I can click on file name. So I can select the particular file and double click it. So the data will be selected here. So similarly, once you select the data, this is for analysis properties. When you when you draw the path diagram, and you can use the analysis properties. This is for calculator estimates. So this is for copy the path diagram to the clipboard. Once you are done with model, if you wanted to save the model, you can just click on this icon. It can be copied, on the clipboard. You can paste it in your Word file wherever you wanted to do it. Similarly, this is for save the current path diagram, and this is what the object properties. These are all I'll explain. I'm just giving an indication of what are all these different types of icons. These are for view smaller areas of the path diagram. It actually enlarges this, right? These are all show the entire page on a particular screen. So when we are actually practicing, you will get to know about all those icons, right? So I'll stop sharing this. We'll learn all those important icons while we are doing it. So let me go back to my presentation here. Yeah. So there are different symbol notations which are very having very different meanings. So for example, if I draw an ellipse and draw a single-headed arrow and draw a rectangle, so like this as the first picture, which basically indicates I'm showing a path coefficient for regression of an unobserved variable on an observed variable here. Because here you see that this particular rectangular shows that uh, observed variable, whereas this shows this unobserved variables. Whereas when you draw both the unobserved variables like ellipses, it shows that the path coefficient for the regression of one factor on the other factor. So you are not talking about a particular item to item. Here you are talking about the overall latent factor to latent factor. So when you have the icon directed towards rectangular, it shows that a measurement error, there is a measurement error associated with this particular observed variable. So similarly, when you draw a single-headed arrow to unobserved variable, it shows that there is a residual error in the prediction of this unobserved factor. So again, these are four important symbol notations are very, very important because it has several meanings. Because every time you look at the picture, without looking at the theoretical part or the explanation, you should be able to identify what the author or whichever author is talking about a particular model, you should be able to recognize it. So here, this is how you draw the diagrams, both observed and the latent variables. So for example, here you have this MSC and MATH. I consider these are the two important latent factors. I say I wanted to measure, there is math self-concept, there is math achievement. So I have labeled this MSC as math. So in this particular picture, I had three observed variables, which I had SDQMSC, which measures basically this math self-concept. And also there is APIMSC, which is another item which measures the math self-concept. And also this particular third item also measures. So you see that these three items measures the math self-concept, and this is the latent factor. These three are observed variables. Similarly, for the math achievement as well, I have this two items which measures the math achievement. After that, not only this, you can also see that there are bidirectional arrow I have drawn here, and also there are error one, ERR 1, 2, 3, 4, 5, and there is a residual 1. Because why do I draw this? Because you need to identify what is your exogenous variable, what is your endogenous variable. Exogenous variable is basically your independent variable, whereas endogenous variable is your dependent variable. So for example, in this particular path graph, you can see that there are two unobserved factors as I mentioned, and also there are five observed variables, both math self-concept as well as the math achievement. These are the five indicators. So whatever these items is basically what you call it as either observed variable or a manifest variable or an indicators. So these five indicator variables actually measuring two latent factors. So here, as you can see, there are associated error terms for each of the observed variables, where you can see error 1 to error 5. And with the factor being predicted, because here, as you can see, the math achievement is my dependent variable. So what I'm showing here, through these items, I'm measuring through two items, I'm measuring the math achievement, and through another three items, I'm measuring the self concept, math self concept. So here I'm looking for the impact of, or the influence of this math self concept on the math achievement. So here the math achievement become as an outcome variable or a endogenous variable, or you simply call it as a dependent variable. Whereas the math self concept, where you can call it as a predictor variable in the regression language, or in the sum language, you can call it as an exogenous variable. Nothing but this is an independent variable. So there is an important distinction between these two terms. Though all those residual error one and these error terms have this ellipses, the error associated with these observed variables, especially this SDQ MSC or API MSC and these five indicator variables, represents that there is a measurement error. All right. So this particular resid one, which measures the residual error. What is the meaning of residual error and the measurement error? The basically measurement error derives from the two sources. One is the random measurement error. So for example, it is possible. So for example, when you give any particular tool or a number of questions to the participants, if there is fundamental flaws in your questionnaire, all right? So this account for the random measurement error. There is fundamental error in your questionnaire design. And there is also another one which we call it as an error uniqueness or uniqueness. So this error uniqueness is an error variance arising from a characteristics which is considered specific or unique to a particular indicator variable. So when you draw a unique error, which means that there is a particular specific error or a characteristics which can be indicated to this any of this indicated variable. So such an unique error variance often represents systematic measurement error because it systematically influences your latent factor here. That is the reason we call it as a systematic measurement error, or you call it as a unique error variance. So the second one, the most important one, which is the when you draw a residual error to your outcome variable, which is your endogenous variable, represents the error in the prediction of endogenous factors from an exogenous factor. So what happens here? The residual term shown here represents the error in predicting the math achievement. So for example, when here we are trying to predict your math achievement from your math self concept. So when you are predicting that there is a residual error, there is something that cannot be directly accounted for from MS, this math self concept. There is something which is residual, which means there is something remaining that you cannot account from these three terms or these three indicator variables of MSC. So that is why we show that there can be something residual error that has an impact on your or predicting your math achievement. So that's the reason this residual error will always attach with the your endogenous variable or a dependent variable, whereas both exogenous variable or endogenous variable can have this measurement error. So here, when you might have observed this. So for example, every time we are drawing an arrow from latent variable to observed variable. So for example, why do the arrows basically goes from the unobserved variables to the observed variables here and not the other way around, which is most important? Because what does it mean when I indicate an arrow to my observed variables? So in some, basically in structural equation modeling, arrows indicate that we are talking about a causal effect here. So the latent variable is typically understood as influencing from the observed variables. So meaning here, so when I indicate an arrow to my observed variable, so the latent variable it comes from understood as influencing my observed variables. So that is why we call it as sometimes the reflective model. Since the observed variables are thought to reflect the underlying latent variable in the model if the model is true. So if the model as you expected, as you draw, as you hypothesize, if the model is true, then we expect that these observed variables are thought to reflect the actual underlying latent factor. That's the reason we call it as a reflective model. So here we need to understand after knowing this basics, difference between measurement error and the residual error and the exogenous and endogenous variable. Let us actually start understanding what do you mean by structural equation modeling, what are the characteristics, and what are the different concepts. So for example, causality and mediation, moderation. What do you mean by measurement model and structural model before we actually learn how to do these things? So for example, here the structural equation modeling is a statistical methodology which takes a hypothesis testing approach, which means that there is a confirmatory approach to our analysis of a structural theory bearing on some phenomena, which means whenever we are reflecting or thought of creating a model, we represents a theory or we come up with some theory. We assume that this theory represents the causal processes which generate observations on our multiple variables, right? So there are latent variables and the observed variables. So the latent variables which we thought that based on our observed variables are manifested variables, we think that we can measure this the causal processes. I know which variable influences the on the which other variable. The basically the term SEM or a structural equation modeling conveys two important aspects of the procedure. The first thing is here the causal processes under the study are represented by a series of structural regression equations. It's basically which is an extension of the regression. In the I think in few minutes I'll explain why we do the structural equation modeling, why we prefer structural equation modeling rather than the regression. Because regression has a different reasons that we use it, whereas structural equation modeling, we use it for several other reasons. So here basically what we expect is the causal processes under your study or cause and effect that what we intend to draw are represented by a series of regression equations. So these regression equations or the structural relations can be modeled pictorially or graphically to enable a clear conceptualization of the theory under your study, which means that which particular variable is leading to other variable, which variable is working as a mediator, which variable is working as a moderator. So all those things can be drawn beautifully, pictorially or graphically in the structural equation modeling. So here the hypothesizer model, once we hypothesize by pictorially drawing, it can be tested statistically in a simultaneous analysis of the entire system of variables. Because what is the difference between regression analysis and the structural equation modeling is every time you are doing a regression model, if you have a multiple dependent variables, you cannot do the multiple regression analysis. But at the same time, though you have a multiple dependent variables or endogenous variables, you can easily do a structural equation modeling. That is one advantage using the structural equation modeling. So here, once the hypothesizer model is using statistical techniques, using the simultaneous analysis of the entire variables to determine what is the extent to which it is consistent with the data. So here you use different goodness of fit indices, especially if the goodness of fit is adequate. Then you argue that through this model argues for the plausibility of postulated relationship among the variables. There are different goodness fit indices will be there that I'll explain, like CFI and GFI and other chi-square and other parameters. If these are adequate, we say that whatever the model we draw, we argue that there is a postulated relations among these variables. If you found the goodness of fit is inadequate, then the tenability of such relations or structural relations or regressions will be rejected based on our analysis. Here, there are 5 important characteristics for this SEM. Excuse me. The first characteristic of structural equation modeling is, as I mentioned here, it takes a confirmatory approach to data analysis, or rather an exploratory analysis. So because that's the reason we have, two types of factor analysis, right? Exploratory factor analysis and the confirmatory factor analysis. When you develop a new tool, we go with the exploratory factor analysis to see that those factors are explored, whatever we initially thought. Once we are able to uh, manage that there is an exploratory factor ability, then we thought of confirming using the confirmatory factor analysis. So it is always goes with hypothesis driven approach or a confirmatory approach. That's the primary characteristics of SAM. The second thing is, it requires a specifying the pattern of intervariable relations or intervariable relations a priori, making it suitable for both inferential purposes as well as the hypothesis testing, where we wanted to test our hypothesis based on the pictorial or the graphical the model which we had. The third one, other than this intervariable relations or hypothesis testing, it also provides several estimates of error variance parameters, with residual error variance or measurement error variance, which allows basically for assessment and correction of measurement error. So the fourth one, it avoids inaccuracies from ignoring errors in explanatory variables, because unlike traditional methods like regression or the general linear model, which basically assumes such errors just vanishes out, but some it does not expect that it vanishes. It avoids such any inaccuracies or errors. So the fifth one, the most important one, it incorporates both your unobserved variable as well as the observed variables in your data set. So the regression analysis, you cannot do that, right? Both latent variable and the observed variables. So these are the 5 important characteristics for this SEM. And after learning this, there are 3 important key concepts in order to understand the applicability or application of our structural equation modeling, which is causality. Because the causality or cause and effect has different meaning, especially in actual experimental studies and this particular structural equation modeling. So because you need to understand primarily, whenever we are using structural equation modeling, we are not manipulating any of our independent variables. We are not having like traditional experimental design, a control group and experimental group. What we do is, the most of the data in which where we intend to use this SEM is applied to collect using a correlational procedure. So for example, you can say correlational design or a cross-sectional design, meaning we collect the data, all the variables were collected simultaneously under the same conditions for all the participants at a time, right? So there is no possibility for you in such situation to manipulate your independent variable, because you are using a correlational procedure or a cross-sectional research design where you collect the data at a time from all your participants. In such a situation, as I mentioned earlier, when you compare with the cause and effect in actual experimental design and the in some related concepts, the research methodology would not support drawing such causal inferences from the study, because research methodology does not support the idea. But here, the question is, how do we get from the research method that say would not support drawing the causal inferences, because here we are not having manipulation of your independent variable and withholding this manipulation of this control group and experimental group. Like how do we get from this scenario of the research method uh, not supporting or drawing causal inferences to a statistical procedure which allows researchers evaluate the direction of influences. So, for example, whether it is a weak causal inference or a strong causal inference in a path model. This is what the most fundamental questions, because I said it is not, we can't actually draw cause and effect uh, like as an actual experimental and control group design, but we can also see this causal inferences. So, for example, let us try to understand this causality as an inference. So let us start with this principle, like, that causality is not present in any actual observations or any data of any piece of research. That is, we cannot directly observe or measure causality itself. So, for example, when you direct your hand to a pencil on your desk and you move it, as an observer, I may know that it was your effort that caused the pencil to move, because I have seen that you have moved your hand, you have extended your hand, like, to pick the pencil. So when I see the pencil moving, that I know that is your effort that caused the pencil to move. So here, what as an observer I see as a sequence of two events. One thing, you are touching the pencil and it is a subsequent movement, right? So here, you can remember the eminent British philosopher David Hume made this case more eloquently, explaining this whole phenomenon. Causality is an inference. So, for example, here David Hume argued that all we see or can observe is a co-occurrence, what we now call is a correlation or a covariance. So, for example, in the earlier example, I said that when I saw you moving your hand, right, directed towards pencil, when I saw the pencil is moving, that I see that there is a co-occurrence, right? So this is what the David Hume has said, that this is what we actually observe. When I see you touch the pencil A, then see it move the B like pencil, the former, which I call it as the cause, which means that your movement of hand, which I call it as a cause, and the moving of the pencil, the movement of the pencil, I call it as an effect. So here, the Hume proposed that experiencing such sequences repeatedly throughout our lives provides us with the sufficiency condition for causality, right? There is a necessity condition, there is a sufficiency condition. So when I observe multiple times the people doing this, multiple times the pencils are moving, then I say that there is something called a sufficiency conditions for me to assume there is a causality, meaning you present A condition and the B occurs. So that is, the presence of A is sufficient enough for B to occur. That is what we basically call it as a sufficiency effect. Whereas, in addition to this sufficiency, Hume also suggested that we also need a condition known as necessity. We say that A is necessary for B if its absence is also associated with the absence of B. Meaning, when you are not, directed your hand towards a pencil, right? The pencil had better not to move because you are not touched it. Like, there is a necessity condition. In order to pencil to move, you should have touched it, right? This is the necessity condition. So here, based on the David Hume's analysis, in many ways, it captures the logic of the scientific method. Because in order to say that some observation is scientifically proven, so for example, consider the conceptually simplest experiment as I mentioned here, where in the experimental design, where you have one experimental group and one control group minimum, and you will present a treatment to your experimental group or manipulation. some manipulation of your independent variable to your experimental group and not to the control group, and you assume that with all other conditions being comparable, you see that any change in your experimental group, you try to assume that it's your manipulation of your independent variable that caused a change in your dependent variable. So that is what we say here. Any difference between the two groups can therefore be attributed to the degree of certainty to the treatment effect. So which meaning we draw the inference that the treatment has likely caused the two groups to be different. Meaning the actual experimental group designs or experimental designs, the experimental group represents both the sufficiency condition because there is a presentation of treatment and obtain a certain effect. So it has the sufficiency effect for experimental group. Whereas the control group condition represents the necessity condition because you know that you withheld this actual manipulation or a treatment to the control group, you withhold not A and the effect not observed B. By establishing this both necessary and sufficient conditions, we are in a relatively strong position to draw the inference the treatment causes such and such effect when it comes to the experimental designs. But here, a correlation design, basically when it comes to this sum and other correlational designs, it does not permit us to observe behavior under the necessary and sufficient conditions because as I mentioned earlier, we collect data at a time. We use a cross-sectional research design or a correlational approach to gather the data. So here we cannot systematically present something and withhold a particular treatment and see that whether A causes B or B causes C. But basically what we see here is a correlation data, is a covariation to a certain quantifiable extent. So for example, the moment I say one variable increase, does the other variable increase or decrease? So for example, whether those two variables co-varies. The moment when I intend to study, the amount of time you spent on social media, like platforms, your academic achievement. So I wanted to see that whether the more time you spent on your social media platforms, whether your academic performance goes down or increase, so you can only see the covariation. So that is what this correlational designs can be done. So here A and B together with many other variables can be related to each other. So here what we do is in causality, we can assess the degree to which each pair of variables, like say for example, as I mentioned here, the amount of time you spent on social media and your academic achievement, you wanted to see that whether these two, what is the extent degree these pairs of variables co-vary. Although we cannot draw any causal inferences here, but covariance can present us with a rich data source. So with this particular data source, because there is a covariation, the structural equation modeling leverages this richness because there is a covariation principle. So for example here, measuring a set of variables within a theoretical framework and then structuring them in a configuration which follows researchers to form and evaluate models which specify certain directions of influence. So for example here, I might say I have three variables, right? So for example, I have a job stress and I have burnout and I have emotional exhaustion. So here I wanted to see that these are the three important variables, three latent factors or the measured variables. I wanted to see that how the direction of job stress on directly stress effect on the burnout, and also how this through emotional exhaustion, how it impacts the burnout. So here, which follows the form and evaluate models which specify certain directions of the influence. Say here, the drawing a causal inference from a path analysis may not be as strong as drawing an inference based on experimental methodology. That's the little bit of limitation when we draw, but here our intention is to prove our point, because we have withheld something and we have seen the effect. What we are trying to see that, because as David Hume's analysis, we wanted to see that repeatedly when we see that there is a movement of something and there is a change in other thing, how these covariances takes place. So that is what basically the causality. However, though the covariation or the does not work like experimental designs, by demonstrating that the model hypothesized by the researchers is consistent with the data, can be taken as support for the model. If I say that in my earlier example, stress can lead to your job, stress can lead to your burnout. But what if you are emotionally exhausted? If I say that as an emotional exhaustion as a mediator, and how strong or weak your burnout, right? So that I can hypothesize the model and I can see that if this model is consistent with the data which I collected from my participants, then I can use this to support for my model, like to show that there is a causality, right? So how this causality in SEM works? So here in the SEM does not prove the causation, but what it does, it only tests whether your data are consistent with the causal structure which you have hypothesized. So, for example, here you draw arrows to represent assumed causal directions. So, for example, stress to burnout. All right. And here the model checks if stress really causes burnout, and does the pattern of correlations in my data fit this assumption. So, I can check by drawing this causal inferences, stress leads to burnout. I can actually test these important questions. So the causation in SEM is always theoretical, because I say it follows as a hypothesis driven approach, or a priori, which is assumed, never statistically proven. All right. I wanted to test whether my model fit as I thought, as researcher, as I assumed. This is what the most important aspect of the SEM for causality nature. Then other two important characteristics, which are mediation and the moderation. So the here mediation meaning, which is an indirect effect. So for example, the mediation always try to answer, does the variable M, in this sense, emotional exhaustion, carry the effect of X on Y? Right? For example, when I had this, my X is job stress, my Y variable, which is my outcome variable, is burnout, and my mediating variable is emotional exhaustion. I can simply draw like this, and there is an X variable and Y variable, there is a mediating variable. So here I can test direct effect, indirect effect, and the total effect. This is what you call it as a simple mediation model. You can actually test this using this SEM analysis. Nowadays the people are also using this the Hayes process macro models, if you just wanted to test this mediation. So what is this direct effect? So direct effect is denoted as a C prime, where you put C apostrophe there, like the C prime. So what is the C prime? Is the direct effect is the stress to burnout. So the direct effect is a direct relationship between your independent variable, which is your job stress, and your dependent variable, which is burnout, in the presence of your mediator. So because there is also mediator, emotional exhaustion is available. But this particular direct effect is the adjusted direct relationship between your job stress and your burnout after controlling the mediator. Though the presence of mediator is there, that here when you are looking for a direct effect, you control the mediating effect, the controlling the mediator, and see that after controlling, what is the relationship between your stress and burnout. It basically represents that whole direct effect, the remaining influence of this stress on burnout that is not explained by the emotional exhaustion. That is what you say the direct effect, or a C prime. So whereas you also have this indirect effect, meaning through your mediating variable, which means that there is A and B relationship, you can see that stress to emotional exhaustion to burnout. That what you call it as the mediation part. Here in the indirect effect is an indirect effect of the relationship between, or it flows from your independent variable to your mediator variable, then your mediator variable to the dependent variable. Say independent variable to mediator, what you denote as A, and your mediator to the dependent variable, what you denote as a B. So it's basically indirect effect is the C minus C prime, which is total effect minus direct effect, which is equivalent to the indirect effect, which is A multiplied with your B, which is A here again, your independent variable to your mediator, and B equal to your mediator variable to your dependent variable, which quantifies basically how much of the total effect is mediated. All right. So this is often tested for various significance tests. So for example, you use the bootstrapping approach. Some people also use the Sobel test to confirm the mediation, whether the mediator has got any effect. If you can prove there is an indirect effect, so which means that the mediator is at work. All right. So the finally, you can also see this total effect. Again, this stress to burnout. But what is this? How it works? The total effect is the combined influence of your direct effect between two constructs, which is your X and Y, and the direct effect flowing through your mediator, meaning your total effect is indicated as capital C. This total effect is equivalent to or equal to your C prime plus A multiplied B. So this is the unadjusted or a total direct relationship between the independent variable and dependent variable, ignoring the mediator entirely. So here when it comes to the total effect, you ignore the mediator entirely, but where in the indirect effect, sorry, in the direct effect, you control the mediator variable. So basically the total effect captures the overall impact of stress on your burnout without accounting for any explanatory role of your emotional exhaustion, which is your mediator variable. So the mediation is basically these to identify these indirect effects. So here you will also come across the words like full mediation and the partial mediation when you actually read path analysis research articles, irrespective of your subject domain, whether it be psychology or management or any other field. So the full mediation is basically the direct path which from your X to Y, which is stress to burnout, becomes non-significant when the mediator is added, which means that when you are looking at the total effect, when you added a mediator, so which becomes a non-significant, your direct path. When it comes to the partial mediation, the direct path is reduced, but still you can see there is a significant amount of variance here. So basically, you can say the structural equation modeling is an excellent for testing mediation because it calculates both the indirect effects and gives the significance test. So for example, bootstrapped confidence intervals and the Sobel test scores to just to see that how this basically works, right? This is about the other important, element, which is the mediation. The last one, we have this moderation. What do you mean by moderation here? The moderation tries to answer the question, does the strength or direction of the relationship between X and Y depend on another variable called M? So for example, in the earlier model, I was talking about stress, mediator, emotional exhaustion, and the burnout. If you are highly emotionally exhausted? What is the strength and direction of this on your burnout? This is what is basically checks using the moderation. For instance, you can use another example, the effect of work hours to burnout is stronger when job control is low. So for example, when you see that it is something like, internal locus of control. you think that you do not have any control, like in your job related things, and it can work as stronger when job control is low. When this control you felt, internal locus of control is low, you can see high burnout among your participants. So in sum, the moderation is usually modeled by creating an interaction term, especially your work hours multiplied with your job control, and letting it affect your burnout. So how many works you are working multiplied with how much your job control is there, and you see that how much it is actually affect your burnout. So here the moderator is a job control. So their mediator is an emotional exhaustion. So this is how this causality, mediation, moderation works, right? So here uh, we move on to there are two important submodels of SEM, which we call it as measurement model as well as the structural model. So here, uh, the measurement model basically defines the relationship between your observed variable and the unobserved variable. So this is what the most important for you to remember. So for example, when you say the moment I am using a measurement model, meaning you are testing your relationship between your observed variables and unobserved variables, meaning a latent factor or latent variable or a factor. In other words, it basically links on a measuring instrument, which is the observed indicator variable, and the underlying construct, which are designed to measure. Probably, so for example, when I'm measuring intelligence, the items which are there in intelligence scale is thought of having an indicator variable or a manifested variable. The underlying concepts that I'm measuring intelligence is a latent factor. So here the model, the measurement model represents the CFA model. So the moment when you heard the measurement model, you are basically using the confirmatory factor analysis model, because it specifies the pattern by which each measure loads on which factor, right? So for example, in my first example, which I was talking about math achievement and the math self concept, where I was talking about three indicator variables or observed variables on, like math self concept, and two observed variables on the math achievement. So I wanted to see that which of these patterns or which of these items are better loading on my latent factor, which is on math achievement or the math self concept. So here, in contrast, if you had this structural model, it basically defines the relations among your unobserved variables.
Participants kindly wait.
Good evening, sir. Your voice is at mute, sir. We are not able to hear you.
Okay, thank you. Thank you. I think in between there was a glitch of my internet. Am I
Yes,
audible,
sir.
sir?
Yes, sir. Yes, sir. Now it's audible.
Okay. Ma'am, can you confirm when did I left actually meeting?
When did miss?
Meaning, how long back? Which slide on? Which slide I'm talking about it? When I'm left the meeting, was I there till the end?
No, sir. No, sir. Last time. CFA part, sir.
CFA part,
Yeah.
meaning, uh, did I? Did you all can hear this structural measurement model and structural model?
Just started, I think, sir. That
Measurement
one.
you are discussing, sir.
Moderation measurement you were discussing.
Which one, ma'am? Which one? 1%, please.
Structural measurement model, sir.
Oh, measurement model, right?
Yes, sir.
Okay, okay. Thank you, thank you. Can you all see the my PPT now?
No, sir. PPT is not
No,
visible.
sir. No, sir.
Okay, 1 second. Let me share. Thank you, Niharika, ma'am. I'm just trying to share my PPT. Madam, it says that the host is not allowing sharing for this meeting. Anisha, ma'am, or anybody who can give me that sharing option?
1 second, sir.
Yeah.
Jayshree, ma'am, whether you can make sir as co-host, ma'am?
Ma'am, I am co-host only, ma'am. Actually, host can only make us.
Okay, let me check, ma'am. 1 second.
Okay.
I think that it says Kristu Jayanti deemed to be university is the host, ma'am. Anisha, ma'am?
Sir, 1 minute, sir. The host is coming. He will make you the
Oh,
co-host.
okay.
Sir, you can start, sir.
I can start. Okay. Yeah, thank you. I guess this is where I left meeting because of my internet glitch. Am I right?
Yes, sir.
Okay. Yeah. Thank you. Yeah. As I was talking, there are two important submodels in structural equation modeling. What we call it as measurement model and the structural equation modeling. Structural model. So what is the difference between measurement model and structural model? So basically the measurement model defines the relations between your observed and unobserved variables, which means that when you are showing a causal relationship between your manifested variable to your latent factors, then it is called as a measurement model. So for example, I was talking about in my first example, I mentioned that the math achievement and the math self concept, respectively, they had 2 and 3 items. So the each was items which was mentioned in the rectangles was actually the individual items, which I call it as a observed variables, where this mental math achievement and the math self concept is the latent variables. When I'm drawing a causal path between these two, then I call this as a measurement model. So basically, when the moment when you say measurement model, you are actually talking about the confirmatory factor analysis model, because here you specify the pattern by which each measure loads on a particular factor. So which each of the observed variable loads on a particular factor or a latent variables. So here, in contrast, the structural model defines the relations among the unobserved variables. You need to remember these two differences very much clearly. So when you are talking about confirmatory factor analysis or a measurement model, you are trying to see the causal relations between observed and unobserved variables. But here you are looking at the between the unobserved variables. You can also call it as one latent factor to another latent factor, or another one factor to another factor. So because here in the structural model, which try to specify how a particular latent variable directly or indirectly influences or can cause a change in the values of certain latent variables. So for example, here in the previous example, when I was talking about this math achievement as an endogenous variable and the math self concept as an exogenous variable, if you are only trying to see the causal inferences between these two latent factors, I think structural equation model is the better model. So here, another clear difference that you can note it down is that the moment when you say measurement model, you are basically understanding or trying to figure out how well your questions measure the construct which you are taught, right? Be it intelligence, be it workplace bullying, be it job stress. Whereas the structural model, you're trying to find out the causation, mediation, and moderated relationship among the those latent constructs or the factors. So basically, the moment when you say structural equation modeling, it combines both measurement model as well as the structural model. Meaning, first we make sure in the structural equation modeling, we make sure to construct our constructs are well measured, which means that through our confirmatory factor analysis, whatever the tools which we have developed or the questionnaires we have developed, these are well measured. Then we test these causal theories, including mediation and moderation, in the structural equation modeling. So here you can see the whole thing beautifully in this picture. So for example, here, when you look at this picture measurement model, when I'm dealing with this CFA, I can deal with two different measurement models. If you see one big rectangular, I'm talking about only this math self concept, which measured through three different items. And if I'm looking separately as this your right side math achievement, which was measured through two observed variables, the latent variable of math achievement. I've talked about, I say these two are two different measurement models or a confirmatory factor analysis. If I combine both, right, when I put this, what you call this oval shape or, oval shape, then I call this as a structural model, because I'm trying to find out the relationship or the causal relationship between these two latent factors called math self concepts and the math achievement. Right? These are the difference between composition of measurement model and structural model. So as I mentioned here, considered separately, the element models within each rectangular in the figure represents two CFA models. The enclosure of the two factors within one ellipse, right, or oval shape represents a full latent variable and thus would not be interest of any CFA research or a confirmatory factor analysis. So here, as I mentioned, the CFA model to the left of the diagram, which you are talking about the math self concept, was measured by three variables: SDQ MSC2, SPP MSC, whereas the CFA model on the right represents the other factor, which is the math achievement. So what we are going to do is, in the next few classes, especially tomorrow, we will be doing the path analysis. So first I'll explain how to draw clearly. Like, I will share the data file which I'm gonna use it. I hope everybody has, AMOS in your systems, like in order to learn perfectly. Like,
Yes,
whatever I
sir.
draw. Sorry.
Yes, sir. Everyone is aware, sir. Also, sir.
Yeah. So I'll share those data before the class tomorrow. So when I draw this, you can learn it hands-on experience. When do we, because we learned so far how do you draw path analysis, path diagram, and how to actually do it. And day after tomorrow, we will use this measurement model, which is confirmatory factor analysis, using another data set. Then the final day, which is Thursday, we will use the full model called the hybrid model. So both the theoretical aspects as well as the most of the theory we have covered today. Then tomorrow we start with the path analysis directly after explaining few basic things in the path analysis. These are the agendas for the next 3 days. I'd like to stop here. If you have any questions, I would like to take it. Right? And we'll continue from the path analysis from tomorrow. Too much of information also may not be good. It will be overloaded, because tomorrow we'll be having 1.5 hours to do it perfectly. Any questions?
Sir, there is a question in the chat box.
Yes.
What is the difference between structural equation model and simultaneous equation model?
What is the simultaneous equation model, ma'am? We call it as a hybrid model, right?
No, Dr. Shankar Mulahun have asked that question.
Dr. Shankar, can you elaborate your question if you are here? Madam, what I was said earlier, like, when we are doing in the structural equation modeling, we do simultaneously, like, that both regression coefficients and the structural equations, both measurement model and this. There is no, as per my knowledge, simultaneous model. What we call it as a hybrid model, where we combine all these, measurement models, right?
Sir, one more question. Can we
Yeah.
test any new construct or unverified variable with the help of SAM?
we can do it provided your data is normally distributed and met other constructs, because every data set has got certain assumptions, right, ma'am? If you have a data, I would like to do it. Otherwise, I have a data which already tested, because when I'm teaching it, because I need to see that, run in and see what are the mistakes, or whether the data set is meeting all the assumptions or not. For example, if you have a new data set, whether there are correlations already existing among all those variables, whether you tested exploratory factor analysis. So for example, if I wanted to run the confirmatory factor analysis, if you had already established an exploratory factor analysis and there is a perfect data, I can run using that particular data set. I don't have any issue. Please provide the data. All right. Otherwise, I have my own data sets. It's not mine, which is already well tested and publicly available data, that which I'm gonna use it. Because unverified data which is not available with me, ma'am. Over, if you have any data set that you are collected, I'm so happy, I'll be happy to do it.
Sir,
Shubham
actually, I
sir
want
is
to know.
asking, yes. Sir, you
Yeah.
can ask, unmuted.
Yeah.
Sir, actually, I want to know that I can test this data
You can.
if I didn't run EFA.
Sorry, sir. Go again, once again.
Actually, I want to know that if I didn't run EFA before,
Yeah.
then in that situation, I can apply SEM or not?
You can apply. You can apply.
Like
It is not.
SEM is always good with CFA.
Yeah. Because the idea is, sir, it is not mandatory you should have done, right, EFA. When EFA is required in order to do the CFA, which is confirmatory factor analysis. If you wanted to directly observe structural equation modeling, it is not necessary you should do exploratory. But only thing is, you need to test the data. Is there any missing data is there, or your variables, what are the data set, whether you are collected data using Likert scale method or ordinal squaring or maximum likelihood method, because each data set is required certain method for us to select. So for example, if you are having an ordinal data, we need to select the ordinal least squaring method. If you are collected data using a Likert scale, I can use the maximum likelihood method. So it is not mandatory for use to SEM. You would have done exploratory factor analysis. Yeah. If you are using a measurement model, yes, CFA, it is always good exploratory factor analysis is established, because here we are trying to test the hypothetical model. Yeah.
Thank you, sir.
Yes.
Anisha ma'am?
Jayshree ma'am.
Yes. With that, we are concluding today's session. We will just continue in tomorrow's session, which will start sharply at 4:30. Tomorrow, there will be a hands-on training in Amos. Thank you so much. Thank you so much, sir.
Thank you, ma'am.